Alright, so this is the video key for the problem set on circuits. Going over some different electrical devices, how we can calculate unknowns, and how we can calculate their cost to use. Okay, so for any of these devices that we're looking at, I do think it's important to stress that they're all electrical circuits, right? They all have a voltage source, which is the outlet. They have a continuous conducting pathway, which goes from one side of the outlet through the machine or through the device, and then back to the other side of the outlet. And they have some sort of resistor, right? Something that converts that electrical energy into some other form of energy. So these are all just slightly more complex circuits than what we've analyzed or what we've built so far in class. So one thing in our house that we could look at is a dryer, for example. And a dryers actually require very high voltages, and they use a lot of energy every second, especially when you run them on high heat. So this one consumes a maximum of 5,600 watts. So that's 5,600 joules per second when you're running it on high heat. And it operates at 240 volts. It actually has a special outlet. And if you look behind your outlet, or behind your dryer, it's got a slightly beefier, bigger outlet. It's a 240 volt outlet. Other devices have that in your household, like ovens, for example, if you have an electric stove. So that's what we know so far. So we know the voltage, which is 240 volts, and we know the power, which is 5,600 watts. And a lot of these devices will have some of this information on them, like our light bulbs, for example, said the voltage and the power on them. Your dryer may say it on the cord somewhere, or it may be on the information that comes with it when you buy it. But we can use these then to find our unknowns. Let's say we also want to know the current going through our circuit, going through our dryer, and let's say we want to know what is the resistance of this dryer that it offers. So in this first part, let's go ahead and try and solve A on this page. We'll solve B on the next page. So we want to try and find current and resistance. Well, there are two equations that we've learned so far that we can use for this. One is Ohm's law. Current is voltage divided by resistance. So for a given circuit, the current going through it is equal to the voltage divided by the resistance. And our power equation, right? The power, the energy usage per second for a circuit, is equal to the current going through it times the voltage being applied to it. So those are our two equations that we can use here. Now so far, in this situation, we know voltage and we know power. So let's see, so we know voltage, we know power, we know voltage. So if we look at these two equations, right? This one, we have one known and two unknowns. So we can't solve for current or resistance using this one. But here we have two knowns and one unknown. So here we can actually solve for the current. Let's go ahead and do so. So the current is equal to, sorry, let me keep it in the form that it is. The power, we could rearrange it, but we'll just keep it as is equal to the current times the voltage. So the power is 5,600 watts. That's equal to our current times our voltage, which is 240 volts. So I'll divide both sides by 240 volts. And the current ends up being 5,600 divided by 240. It's 23.3 units for current, which is amps. Right? So 23.3 amps. So that's a good bit of current going through this dryer, which makes sense. With that large amount of power and that voltage, we'd expect to see a pretty high current as well. So now that we know the current, right, we can also solve for resistance here. Now I'm going to go ahead and rearrange this before substituting. So when we rearrange Ohm's law for resistance, we end up getting resistance is equal to voltage divided by the current, right? So resistance equals voltage divided by current, right? The voltage is 240 volts. The current we just found was 23.3 amps. Therefore, the resistance would be 10.3 ohms. Right, so there are my two unknowns for this first problem. The current is 23.3 amps, and the resistance is 10.3 ohms. So a pretty low resistance for something of that size. So that is the first part of number one. And then for the second part, solving here, So many appliances are advertised with energy calculator stickers to give consumers an estimate for their annual cost. Okay, so a lot of times if you go towards like Home Depot or Lowe's or some other store where you can buy these devices, they'll say essentially how much, should it cost you to use for a year. So this one's estimated to cost you only $131 for the year to run, right? Not too bad considering how much power it uses. So let's consider how we then calculate out that cost and how we get that number. Well, if you remember our 4 simple steps to calculate the cost of electricity, first we convert power to kilowatts, then we convert the time used into hours, then we calculate the energy used in kilowatt hours and multiply that cost by the cost per kilowatt hour. Right? So let's start with step number 1, right, which is power to kilowatts. So we have 5,600 watts, and that's times 1 kilowatt over 1,000 watts. Notice watts on top, watts on bottom, they cancel. And we get 5,600 divided by 1,000, which would be, you guys probably could have done this in your head, but it's 5.6 kilowatts. Right? 5.6 kilowatts is the power usage of this. Right? Now, if it is estimated at $131.04, right, we're going to go ahead and kind of skip to step 4 here. Right, so in this case, it's $0.12, so 12 cents per kilowatt hour, right? And we don't know the amount of time that this is projecting that we'd actually use it for. But if we're using it for an unknown amount of time, right, that will give us 131.04, right? So if we divide both sides by this cost per kilowatt hour, right? Or sorry, this shouldn't be time here. This would just be the energy, right? The energy in kilowatt hours. Sorry. So if we divide this side, divide both sides by $0.12 per kilowatt hour, right? What we end up getting is the actual energy used to give us that total is 5.2. Wow, 1,092 kilowatt hours, right? So that's the actual amount of energy that this is projecting that we'd use in a year using this dryer, right? So step 3, kind of working backwards in this one, right? If the energy was 1,092 kilowatt hours, right? And we know, we know that the kilowattage, or the power used by this is 5.6 kilowatts, right? Times an unknown time gives us our total energy usage, which is 1,092 kilowatt hours. All right, so if we divide both sides by 5.6 kilowatts, we should get that the time that we actually used it ends up being 195 hours. Right, so this is projecting that you'd use it for 195 hours. So if we consider that there's 365 days in a year, right? And let's say that you use it for half of those days, so that's 365 divided by 2, right? So that's about 182, is every other day, using it every other day. So, and that's pretty close to our 195. So that's about an hour a day, every other day that we're using this for. All right, so that's how we could kind of solve, and that's how we would use this process here. Number 2. Let's go through this one. So in this case, we have a hairdryer. Some of you guys may use these, or may have seen them, may be familiar with them. And what these do is they essentially have a circuit that involves a heater and a motor, right? Something to convert that electrical energy into kinetic energy, rotating a fan blade, blowing air, and something to convert that electrical energy into a lot of heat. All right, so still just a circuit. If we look at this one, it has a power, rating of 1,875 watts, so that's 1,875 joules per second that you're using it. That's when it's running at full power, so full heat, full speed. And this one is just plugged into a standard outlet, so 120 volts. So once again, let's go ahead and put in what we know here. So we know the voltage is 120. We know the power is 1,875 watts. Right. Now, if you guys haven't yet tried this one on your own, I would say go ahead and pause the video at this point in time and give this a go. Okay, so assuming that you guys have tried this, because it's pretty similar to the last one, we know the voltage and the power, and we don't know the current and the resistance. Once again, we have our two equations up here. We've got the Ohm's law equation, which is current is voltage divided by resistance, and the power equation, which is power is current times voltage. If we look at what we know voltage and power. Right, so here we have two knowns and one unknown, so we can solve for current. So the current power is equal to the current times the voltage. So 1,875 watts are equal to my current times my voltage, which is 120 volts. If I divide both sides by 120, I get a current of 15.625. Right, so also a pretty high current device, right? Pretty high current running through that hairdryer. And this is part of the reason why you want to be so careful with devices like hairdryers around water and wet areas. Right? Because water, if it has kind of salts dissolved in it, can be a pretty good conductor of electricity. And this is a pretty high current. And if you guys remember, it's not voltage that is actually really that dangerous, it is the current. So this is drawing a lot of current from that outlet. That's a lot of moving electrons. And so that could actually end up causing some harm to you, causing some pretty severe electrical shock. So you don't necessarily want to mess with these in really wet environments. It's fine blowing on hair, but you don't want to like slip and fall into the bathtub with it. That would be bad, right? That's why you don't use these while you're in the bathtub. Don't do it. And then if we look at now, we have the current, so we can solve for the resistance. Once again, if we rearrange that for resistance, resistance is voltage divided by current. So resistance here is equal to the voltage divided by the current. The voltage is 120 volts in this case, and the current we found is 15.625 amps. So the resistance for this one is 7.68 ohms. There we go. So that's solving for part A there. Now if we look at part B, right, we know once again what its power usage is in this case, 1,875 watts, and we want to know at the end of the month, right, so we'll say 30 days in a month, if we use it for 15 minutes each day, how much would it cost us to actually run? So we go through our 4 steps, and this one is going to be nice. It's going to be in order, which is convenient. So step number 1, right, we convert our power to kilowatts. So 1,875 watts times 1 kilowatt over 1,000 watts. Watts on top, watts on bottom. Those watts cancel. We're left with just kilowatts. So this gives us a 1.875 kilowatts. Step number 2, we want to figure out the time that we actually use it in total, right? So how much time do we actually use it in hours? So if we use it 15 minutes per day, and so let's say how many hours is that per day? So that's times 1 hour is 60 minutes. Notice here we have minutes on top, minutes on bottom. So now we have This gives us 1 hour every 4 days, or rather, maybe a better way to write that would be 0.25 hours per day. So we have 0.25 hours per day, and that's times 30 days in a month. Notice we got days on top, days on the bottom. And we get that the total time usage per month, right, is 7.5. So we're looking here at 7.5 hours is the actual time usage during that month. So if we want to know the cost per month, that's the total hour usage. So we know the power rating in kilowatts. We know the time that was actually used. So the third part is that energy is equal to that power times time. So the energy usage in kilowatt hours is 1.875 kilowatts times 7.5 hours. So the total energy usage was I'll say 14.06 kilowatt hours. Right, so that's the actual amount of energy that you used, keeping in mind that it's about 3,600,000 joules per kilowatt hour. So that's a lot of energy, using that over the month. And we know for step 4 that it's a cost of $0.12 or 12 cents per kilowatt hour. Multiply that by our usage, 14.06 kilowatt hours. Notice those kilowatt hours cancel, got one on top, one on bottom, and we're left with just dollars, right? If we calculate that out, that ends up being about $1.69. Right. That being the final answer as to how much it actually costs to use. So, not a crazy amount of money, but it's still something. It all adds up. All right, next one here, we're looking at Mr. O'Keefe's desk fan that he uses in his office. If you kind of zoom into this on the assignment, you'll see something in here that says 120 volts is the outlet that you're plugging into, and 0.25 amps, which is the current that this actually draws. So in this case, we have two knowns. We've got the voltage, which is 120 volts, and we have the current, which is 0.25 amps. Right. At this point in time, definitely make sure, if you're just kind of following along blindly, give this a pause and see if you can't calculate out what the resistance and the power would be for this one. This one is actually relatively straightforward. Okay, so looking at our two equations again, we got our Ohm's law, which is current is equal to voltage over resistance, and we have our power equation, which is power is equal to current times voltage. So, looking at this and what we know the current, 0.25 amps, and we know the voltage. And here we also know the current, we know the voltage. So we should be able to solve for both resistance and power already without needing one over the other. So let's go ahead and solve for the resistance first. Once again, if we rearrange this, right, we get resistance is equal to voltage divided by current. So resistance equals voltage divided by current. So that's 120 volts divided by 0.25 amps, which gives us a resistance of 480 ohms. So the resistance in this case ends up being 480 ohms. So a significantly higher resistance for this than the previous two devices that we looked at. And then the current for this one, so power is equal, or sorry, the power for this one, power is equal to current times voltage. So then power is equal to 0.25 amps times our voltage, which is 120 volts. So the power is 30. And what are our units for power? That is, of course, watts. Power is 30 watts. So this thing requires 30 joules per second to operate. So not nearly as much as our previous ones. This one is, of course, taking that electrical energy coming from the outlet, that electric potential, and converting it into kinetic energy in the form of motion. Right? So that's for part A. We calculated the power was 30 watts. So then for part B, right, we already found that the power was 30 watts. Okay, so if we want to know what's the yearly cost to Lusher Charter School, assume there are 180 school days in the year, and each kilowatt hour costs 12 cents. So we run it for 45 minutes each school day. So let's go through our cost of electricity steps. So number one, we convert our power to kilowatts. So 30 watts times 1 kilowatt over 1,000 watts. Watts, of course, cancel. And we're left with 0.03 kilowatts. Right, so not nearly as large a value in kilowatts. The second part is to calculate the amount of time actually used. So 45 minutes. So 45 minutes per day. And we want to get minutes to hours. So that's, of course, 60 minutes over 1 hour. There are minutes cancel. And in this case, we end up with 45 divided by 60, so 0.75 hours per day. And then we want to get that, how many days do we have? We've got 180 school days. So that's 180 days in a year. Our days cancel. And the total hours that we end up using this in a year, so we got 0.75 times 180, 135 hours per year. Right, so 135 hours is the amount of time that we're actually using it in the time frame we're concerned with. Number three, the total amount of energy is equal to that power times time. So the energy that this fan is actually using in that year is our power, which is 0.03 kilowatts, times our time, which is 135 hours. So the energy actually used ends up being 4.05 kilowatt hours. Once again, if we want the cost, the total cost, that's 12 cents per kilowatt hour times the amount used, the amount of energy, which is 4.05 kilowatt hours. And that gives us, notice the kilowatt hours on top and bottom, they cancel, we're just left with dollars. And that gives us not a whole lot. Geez, we'll round that up to 49 cents. So 49 cents is the cost for Mr. O'Keefe to run his fan. So is this going to be breaking Lusher Charter School's bank? Probably not. Probably not. Mr. O'Keefe could just throw in a couple quarters if he needed to, and he could help keep them afloat. And on here to the last problem. So this is something that you guys should be relatively familiar with. Any of your electronic devices that you use, such as iPads, computers, iPhones, any sort of other thing that you plug into the wall and you charge a battery on the inside. Well, those chargers, right, when you're charging the battery, you actually have these little power adapters. And if you zoom in real close on this one, you'll see there's an input and then there's an output, right? The input is what you plug it into. That's a 120 volt outlet. But the output is the thing that we're actually concerned with, because the output is what is actually charging your battery, and that's the electricity that you're actually using within your circuit. So anytime that you see these, we're concerned with the output. And if you zoom in on this one, from Mr. O'Keefe's iPad, its output is 5.2 volts, and it uses 2.4 amps of current. All right, so here we know the voltage and we know the current. Voltage is 5.2 volts and the current is 2.4 amps. So once again, if you guys give this one a shot yourselves, you guys can go ahead and pause the video here and try and find the resistance and the power. So if we look at this one, once again, we got current is equal to voltage over resistance, and power is equal to current times resistance. If we look through this, we know the current and we know the voltage. We know the current, oh, did I say power is equal to current times resistance? Silly me. Current times voltage. And we know that voltage. So this one's just like the last one. We can calculate for the power and we can calculate for the resistance. Let's go ahead and do the resistance first. Rearrange Ohm's law. Resistance is voltage divided by current. So resistance equals 5.2 volts divided by 2.4 amps. So 2.16 ohms is our resistance. So not a very large resistance at all for this device. And then for the power, power is equal to current times voltage. So that gives us our current, which is 2.4 amps, times our voltage, which is 5.2 volts. And that gives us a power of 12.48 watts. All right, so that's actually the power consumption of charging this iPad. All right, that is actually the amount of joules per second that it takes to charge this iPad. So the amount of energy per second it takes to charge this, and so if you charge it for a certain amount of time, that's what we're going to calculate in part B. So here we have 12.48, so we're calculating in part B, so we have 12.48 watts, right? So that's 12.48 joules per second, and we are charging it on full power for 5 hours, right? So 5 hours is our total time here. So calculating out our cost, once again, number one, we convert our power to kilowatts, so 12.48 watts, right? That's times 1 kilowatt over 1,000 watts. Those watts cancel, and that gives us 0.012, I'm just going to round up at this point in time, 125 kilowatts. All right, so not much in the way of kilowatts in this one. Number two, we actually calculate the time used. In this case, the time is pretty easy. We charge on full power for 5 hours. 5 hours, done. Time's already been calculated. And we find the energy in kilowatt hours. Well, energy is equal to power times time. So the energy in kilowatt hours is 0.0125 kilowatts times 5 hours. So the energy ends up being 0.0625 kilowatt hours. And last but not least, we actually calculate the cost of that much energy, knowing that it's about 12 cents per kilowatt hour. And then we got 0.0625 kilowatt hours used. And we get 0.075, which we'll round up to $0.01. Right, so it costs you 1 cent, right? 1 cent to actually charge this thing for 5 hours. So that's pretty incredible that we can actually do that, and then it only costs that much. Now this is, of course, you're going to be charging it for probably more than 5 hours throughout the year, so it could cost you a decent bit as time goes on, but compared to the cost of the device itself, the cost to actually run it and charge it is relatively minimal. So the last thing that you guys need to do is you guys are going to find an electrical device of your own, and you're going to take a close-up photo of that electrical information. So sometimes it's on the cord, sometimes it's on the device itself. Here's one I found for the air pump here, and this one has the power and it has the voltage, right? So you need at least 2 of those things, right? And with any 2 of these, you can solve for the others, but you need at least 2 of those on your information. You might have more, you might have 3, but you're going to take a close-up of that information, and that you're going to use that then. We're going to use that when you guys get back from break to actually calculate how much it costs you to use that device per month. So think of something cool, maybe a microwave, might be a toaster oven, might be your PlayStation, might be something else entirely, right? A hair straightener, something unique that is not, right, like the iPad and not a light bulb, something a little bit different than those 2 things, something new. So that's that. Hopefully you guys found this pretty easy and you guys feel comfortable doing it. And I'll see you guys after break.